This talk is going to be done by Professor José Capmany from Polytechnic University of Valencia. And I will say very few words because he is very friend of mine, so I will say very few words about. So José Capmany, just to put you in the screen, have 2 degrees, have 2 PhD degrees, okay? So it's not very common to find people with several degrees in the same career, and at the same time that he's working with. So Professor Capmany, if is one person in Spain that if you ask for someone that have the more rank in optical communications, rapidly appears the name of Professor Capmany. So, in fact, I must to confess that when I was planning to do this international school with a focus in communications, I called Professor Capmany and I say, please tell me the best worldwide. Okay? So, thanks to Professor Capmany, we have here the best one in communications in these days. Just to say that Professor Capmany is a fellow of IEEE, OSA, and IEEE, and he is prized. He has several very important prizes, but I will only mention one. It is the Jaime the First, the Kingdom Jaime the First prize. That is one of the highest prizes in science in Spain, because the jury is integrated commonly with 20 Nobel Prizes. So maybe Nobel Prize is not about. So thank you for coming.
Thank you.
And it's a pleasure to be here, to see you here anytime.
Okay. Thank you very much. Thank you very much for the very kind introduction. It's good to have friends. Okay, so I'm going to speak about a relatively old and new topic, which is analog photonics. And my background is usually, I have worked for many years in RF photonics, which has an increasing field of application, area of application, but in my opinion is a small part of something much bigger, which might be unleashing in the next few years, which is analog photonics. Okay, so one of the good things of being the last speaker is that some of the smart people have already done some job for you. So I was going to provide some introduction about our need to. Oh, sorry. This maybe it's been okay. All right. I was going to provide some small introduction about why do we need to have good infrastructures, prepare ourselves to have very good infrastructures to face global challenges that we are going to have as far as ICT systems are concerned in the next future. But Peter has done this very nicely, both Peters. So thank you very much. And but I want you to pay attention to the last data on this view graph, which is related to mobile data traffic. Okay, so this is main key results of a study that was published by Cisco a couple of years ago, 3 maybe, and that predicts a very big increase in traffic requirements, and therefore we should be prepared to develop the technologies to have the right infrastructures. Now, I always like to stay at this point in my lectures and think probably there's a famous quote which is attributed to a baseball player, Yogi Berra, who said that the future is no longer what it used to be. And that tries to express that making predictions about the future is very difficult, of course. All right? So Peter has also mentioned the fact that we never know what is going to come. We are ready for what is or we try to be ready for what is already operating, like YouTube or whatever, but nobody has been able to, let's say, forecast what is going to happen, okay? And there are very few areas in research which have experienced so many unexpected, what we call black swans, okay? A black swan is an event that has a massive impact on our lives. And ICT systems have had a lot of black swans. Lasers, portable or personal computers, mobile communications, okay? What is coming next? Nobody knows, okay? So we have to be prepared for that. Now, this is a very important example because it stresses the fact that in a way, we have to be prepared to develop technologies that have to interface very different worlds. And with that, I'm referring to wireless and fiber, okay? They are not very alike, okay? And yet, we need to develop something that makes them couple nicely, okay? In this case, at the base station. Okay, so we need these solutions, and not only for mobile communications, for a lot of services that are on the line of sight that are going to require an interfacing between these wireless and fiber segments in the telecom networks, okay? And then you have some representative examples, of course, the more known mobile phones, but then we have Internet of Things, possibly autonomous driving, okay? Wearable devices. All these are like smaller or bigger data streams that are going to flow and converge into a base station. And the base station has to take account of all of them, in a way manage their spectral placement, they're doing some processing, and then deliver that into the transport network. In some ways, giving more work to what Peter said. Okay, this is like a small rivers that come into the big one, and the big one has to be prepared, but the smaller rivers are going to increase as well. This is one of the main challenges as well. Yes, for example, for those of you who are not familiar, for example, 5G targets an impressive amount in the requirements that wireless systems, if you compare to actual wireless systems. So there are a lot of issues that we have to solve. And of course, it would be nice if we could have something inside here that could interface, any technology that could interface these wireless and these fiber segments. Right, so this is what for many years, okay, let me see. All right. Has been the subject of RF photonics. And in this case, it's going to be even more pushy because, as you see now, there's a shift towards higher spectral regions. In the case of radio frequency signals, we are trying to expand into higher bands, higher spectral regions for 5G, to support 5G, to support automated radar, etc. So that means that we need to interface signals which are inherently in some way analog, because they are going to use some RF analog carrier. Nevertheless, I mean, they are digital in context, but they are, in a way they are going to be carried by an analog microwave signal or RF signal, and we have also to interface that into the optics world. So this is the subject of RF photonics, and RF photonics is let's say the first application of what I like to call analog photonics. But there are other applications that are emerging as well, like neuromorphic photonics, artificial intelligence and deep learning, maybe quantum processing, sensors. And for these applications, you need to have, you would like to have some technologies which are able to process non-digital features of signals, okay? Like, what is the position of a pulse? If you need to process some spike or whatever. And these are other emerging applications which complement what I've been talking before, just the RF interfacing communications, which is by now, and by far, the most important application. So, analog photonics, in principle, is a very good technology, which is one of the best placed technologies to provide this flexible and adaptive physical layer to interface RF or analog type signals with photonic signals. But let me try to explain. Can you raise your hand if you know any, if you don't know what RF or analog photonics is about? More or less the basics? Okay, well, so I can skip the, oh. All right. So I'm going to do something which is very graphic, so it will be very fast. Now, with RF photonics, for example, what we do is we take one signal, analog signal that we get from any radio or analog source or whatever, like you see here, it's like, I express this like two sidebands and in the radio frequency. And in traditional RF systems, what we do is, yes, we pass this through a system that is composed of elements. These elements are usually very bulky, and they're very frequency selective. So, for example, if you have one device for one band, it will not work, will not have the same functionality in another band because it will be band limited. And we try to do something on the sidebands, whatever processing it is, and then we get the processed signal to do some kind, either to receive it or to re-radiate it through an antenna or whatever. This is the traditional RF operation. What we do in analog photonics is we get rid of this intermediate part, which is usually very fixed. It's not flexible. And actually, we upconvert the signal, and we use an optical link to upconvert these sidebands into the optical part of the spectrum. Then we pass this through an optical system, whatever. I call it optical core. It can be as simple as an optical fiber link. And that was the original application of analog photonics, because optical fibers are very low loss. They could transport or RF or millimeter wave band signals through to remote antenna locations. Then we only have to down convert it using the photodetector, and then that would be ready for radiation. So this morning there was like a mention. I also like to put this mention about the Occam's razor. Okay, you say, why are we bothering in getting and implementing a complicated solution when the other one that I explained is very simple? And the reason is that optics provides you with some features that RF systems cannot do. And the most important property of optical systems is that they can be controlled. They are to some extent much more easily reconfigurable through control signals than RF. And they are inherently broadband, of course. So you can use your control signals to do your processing and change. Okay, so but all in all, these systems are quite bulky. If you go through the literature, you will see that there are a lot of proofs of concept. All of them are extremely bulky. They are not very good for being repeatable, and of course, they are not very good for putting it in a small cabinet in a base station. And if you take into account that 5G is requiring us to go into higher bands, then that means that the antenna, everything is going to be smaller. So what you need is to have compressed all these systems into a smaller footprint. And the only way to do it is by integrating. So integration is very important, like in other areas, of course. And it is important because we need space, weight, and power consumption reductions. Okay? So this is what we want to tackle when we refer to integrated analog photonics. So this is more or less like a very small, short introduction to analog photonics. And of course, this can be a radio signal, but it could be a baseband signal as well, but with, let's say, non-digital features as well. You could do a similar reasoning. So talking about integrated analog photonics is a quite recent subject. So in our context, we have been working in the last, say, 5 to 10 years in the first developments of these kinds of circuits. And as in many other fields of photonics, there are 5 main platforms that have been frequently used, but I will reduce them to 3, really, to indium phosphide, silicon photonics, and probably silicon nitride as well. Indium phosphide is a technology which is very good because it's active. It's the only one that provides you active devices and sources, but it's quite lossy, while the technologies that are based on silicon are inherently low loss, but they have the inconvenience that they are passive. And in some cases, you can grow detectors, you can grow modulators, but you cannot implement you cannot grow an optical source there, although there are solutions, as I will try to explain now. Okay, so what we are aiming basically is to find in integration what we call the sweet spot. And the sweet spot is something that is multidimensional. I've just put here like 4 quadrants, but it's really a much more difficult problem to solve. You want low losses in your circuits, low waveguide losses. You want, if possible, to have active operation. You want to have the possibility of electronic co-integration, because no matter what photonics are you using, photonics always need control electronics. Otherwise, it will not be programmable, it will not be reconfigurable. And if possible, you want small footprint, which you may guess, okay, in integrated optics, everything is going to be small. Yes and no, it depends, okay? Not every material allows you small bending radius, etc. So depending on the technology that you use, your circuits can be low footprint, or it can be around several tens of millimeters. Okay, so we have the different technologies. Silicon on insulator is perhaps the most popular one. And it's really, really close to the sweet spot. But the main limitation here is that active operation is not possible as far as laser transmitters are concerned. You can build modulators, current injection modulators. You can do detectors if you put germanium. You can do some active, in quotation, operation, but there's no way of growing optical sources. Then we have silicon nitride, which is similar. It has a better performance in terms of low losses. Electronic co-integration is also possible, but there's no possibility of active operation. And silicon nitride is a low contrast technology, so bending radius are not very small. So your circuit footprints are big. I think I probably, okay. Then you have indium phosphide on the other part of the quadrant. Then you have what you miss in silicon photonics. You have active operation plenty. You have sources, you have detectors, you have optical amplifiers, which you need to compensate losses, because that's another question. If your circuit is passive, then it cannot contain a lot of elements because you need to compensate insertion losses, okay? But then, not very good performance. So what is the solution? The solution now is to go to hybrid or heterogeneous technologies, where you mix 2 systems. Like the most interesting one is probably silicon on insulator plus indium phosphide. And the way that now the people are trying to develop these technologies is that you grow your silicon passive chip, and then you develop technology where you stamp your indium phosphide devices wherever you want. This is a quite promising technology that is already in in some commercial machines, you can also already buy them. Not very high performance, but it will be in a few years. And of course, you can also use silicon nitride and indium phosphide there. So there are some solutions to this, let's say, optimum operation in terms of technology. So that's more or less the path in technology that these circuits are going to follow in the next years. So we will see more and more increasing contributions on these hybrid platforms, not only for analog photonics, but also for other fields of applications. So let me try now to give you some summary. This about the evolution of integrated analog photonics is, in a way, is following very much the path of electronics in the 70s and the 60s and 70s. So first thing I'm going to spend some time is in describing you what we call the ASPIC paradigm, which is very ASPIC stands for application-specific photonic integrated circuit. And the meaning is that you need to do some function, you design an ad hoc circuit to do that operation. Okay? So this is what we call ASPIC paradigm. What you have here is, let's say, a snapshot of different circuits that have been reported in the literature in the last 5 years. So all these are different technologies, different applications. I'm going to try to explain some of the basic features. Now, but in a way, these circuits are tailored for just one specific application. So this will give you an idea of what is the state of the art, in more or less. For, let's say, analog photonic applications, we have a lot of functionalities. You can think about filtering, of course. You can think about phase shifting, true time delays. You need to delay the signals. Perhaps you want to generate a complex signal, RF signal, and you want to generate on a chip and then be able either to radiate it or just deliver by an optical fiber link to an antenna or whatever. Or maybe you want a very precise oscillator and you want to do something, what we call optoelectronic oscillator, which is very much like a laser, but it works in a hybrid configuration, and it produces very high quality and stable radio frequency signals. Okay? There are other applications. So I'm going to give you some summary and about some results which are interesting, so you can get an idea more or less of what is the state of the art. Now we have, regarding filters, we have had a lot. There are lots of papers that you can find, lots of contributions. I have just selected a couple of examples. The example that you have on your left-hand side is a complex filter which is made of cascading different unit cells. The unit cells are here, are simple structures which are basically a ring-loaded Mach Zehnder. And this is like when, for those of you who are familiar with electrical engineering disciplines, this is like combined finite and infinite impulse response filter with one pole and one zero. It turns out that if you cascade several unit cells, then you can program independently the zero and pole locations of all these unit cells, and then you can build up like complex filtering structures. You want to, for example, if you want to do some processing of the signals on the fly without needing to go into the DSP or alleviating the task that the DSP will have to do later, then this is one of the applications of these filters. But of course, this is a silicon chip. I haven't included the photograph because it's not in the paper. But this is a silicon chip, and it does not contain the source. It does not contain the detector. The other one that you see on the right-hand side of your view graph is a monolithic filter, and that monolithic filter it's made of a double ring loaded Mach Zehnder, which you can see here. But the nice feature about this is that it also contains the source. It has two DFB lasers here, a modulator and a detector, and moreover, it's packaged It's an indium phosphide, of course, because otherwise it's not possible to integrate the optical source. And yet, these filters work on. So far, they have had like quite modest performance, but this is due to the fact that this is. Losses are high here, and there are other design challenges to be met. Also, the packaging, which is the housing in which you put your chip once it's fabricated, is not usually designed for RF operation. So these are things that have to be improved. But the challenges here is that if we want to do complex filters, we must be able to have very low loss unit cells, so we can scale a lot of them. Okay. Then we need to have to sort the means to control the program filter parameters. So actually, we place the poles and the zeros wherever we really want to put them. And there's another curious challenge, which deals with packaging, because you are dealing with RF signals. And then you have to put in your package the photonic and also the RF signals. Then you have to be very careful, and you have to avoid the coupling between the modulation and the detection, then the detected RF signals, of course. These are a couple of examples regarding filtering. Phase shifters is a more standard component. You have like two options, like a narrow band and a broadband operation. As it works, for example, the narrow band phase shifter, you can integrate in very easily. It's just a ring cavity, a single ring cavity, and this cavity works as a resonant filter. And in the resonance, what you have is a phase shift, strong phase shift here. So if you send your signal with only one sideband, and you take care of placing for example, the optical carrier in the resonance, then you can, by changing the refractive index of your cavity, you can change the resonance position. So it is the carrier that experiences the phase shift, and when it beats with the subcarrier, with the sideband, then you impress the phase shift, and this is a tunable phase shift. Although this requires, again, the cascade of several elements, because with one it is not possible to get a 2 pi phase shift that you would need for a complete phase shift. So there's another option, which is to avoid resonant devices. If you don't want to have narrowband devices and which are periodic in the spectrum, there's a solution which is to use Bragg gratings. In this case, it's integrated Bragg gratings with a phase shifting in the middle of the corrugation. And that, again, produces like a small dip, a small resonance here with a big phase shift, and allows you, in the same way as I explained before, by placing this is the carrier, and this is the sideband. So you move either your carrier or you move the filter shape, and you change the phase shift that the optical carrier is experiencing, and then by beating, you impress that phase shift on your RF detected signal. So both examples, this is an indium phosphide silicon chip. This is an indium phosphide ring cavity, and there's a silicon waveguide. This one is only a silicon photonics. Okay. We have the same challenges. We have to cascade several elements, so we need very low loss unit phase shifters. Again, we have to have a precise control over in this case, the modulation of the ring cavity. So we have the refractive index and the phase shift that we want, and of course, if possible, avoid the multi-spectral operation. So we have broadband operation. Well, It's going to give you one example more. This is programmable true time delay lines, which are basic elements for doing phase array antenna, beamforming networks, other applications as well. And the way that this can be done is by solving a limitation of integrated circuits. If you have a very small footprint circuit, then you cannot implement a very long path because you don't have enough space. So there are two ways to overcome this method, this limitation. One which is particularly smart, in my opinion, is to use what we call the separate carrier tuning technique. And this means that, for example, whenever you want, let's say you have an optical carrier here, and then you have your information here, modulated and RF. And if you want to have a phase shift, a given phase shift, what you need to have is like a constant slope curve as you have here, okay? So this is very hard to have on a broadband region because the cavities usually don't have enough bandwidth. So the solution to overcome this technique is to design one stage which takes care of the phase shift of your information signal, okay? And then you take advantage that the region in between the analog signal and your optical carrier is void. There's nothing. So you don't need to implement the phase shift here. But you have to take into account that your carrier needs to sense the same phase shift. So actually what you do is you design a phase shift, a delay line operation here, which provides this phase shift, and then you extrapolate the actual value of the phase shift here for your optical carrier, and you do this with a second unit. So you have a two-time delay line by placing in cascade a delay unit only for a narrowband signal and a phase shifter for your optical carrier. So both of them are adapted, okay? So this is like having, in real terms, a complete phase shift over a big bandwidth because, remember, you don't need any phase shift here. So this is what you can do easily with an integrated optics design, and this provides you with a true time delay line unit. Of course, you can increase the value of your true time delay line by putting more cavities in cascade, or either do it also multi-wavelength operation by using Vernier effects. And in this case, you need particularly low-loss waveguide technologies, and this is why most of these works have been done in silicon nitride, because this technology provides very low propagation losses. So with that in mind, if you have these programmable two-time delay lines, it is it's quite easy to demonstrate that this is a true-time delay line, because if you have like two paths here, you put this true-time delay line in an interferometer, okay? So when your true-time delay line is working really as a delay line, when you change your delay, then the spectral period of your filter, or your two-tap filter, changes. This is what you have here. Sorry. You see that you change, there's a slight difference here. This means that the period is different. If you deactivate the delay line and you just operate this as a phase shifter, then your filter will move the resonances but will not change the spectral period. Okay? So this unit is quite useful because you can do both things. You can do a phase shifting element, or you can do a true time delay line. You can combine with more stages to do a much bigger delay or a much bigger phase shift, and you can put on Vernier configurations to do multi-wavelength operation, but not equispaced. With that, for example, you can use these units then to implement beamformers. This is a very nice example that was reported by researchers at the University of Twente. And they use these modules, the 2-time delay modules, to do this 8-unit beamformer. And as you see, they are able to control different incremental delay lines for the 8 units. And with that, they were at the time they were working on a 2-time delay line beamformer for playing to satellite communications. Okay, so this unit had to work on this spectral band in between 10 and 30 gigahertz, and the way they operated this and then demonstrated the operation was, they operated this in 2 ways. One was like a narrow band beamformer, where you just do phase shifting. If you do phase shifting with a narrow band in a narrow band beamformer, what you have is what you call beam squint. That means that the pointing direction of your beam is different depending on the frequency. So this is a limitation, and this is why this technique is only used in narrow band beamforming networks. If you want a wide band beamforming network, you need to have 2-time delay lines. And then your pointing direction will not change with frequency. So this is a very nice example of the pointing direction when they implemented the beamforming using the 2-time delay line. You see, for all the frequencies, the pointing angle is practically uniform. But when they operated this as phase shifters, there was a beam squint. That means, for example, that for a 12.75 gigahertz, your pointing direction is like 25, something like that, while for 10.7 is 33, 34, which is quite different, okay? It gives you an idea of the operation. Okay, I don't want to spend much more time about this, but there are more examples, like in this case, recently reported integrated optoelectronic oscillators. And this is like a laser, but it has an RF part and a photonic part. The photonic part is used as a storage element because it is low loss and it can provide some delay. And it's like a closed cavity. And when you close the cavity, then you have stable solutions that correspond to carriers in the RF frequency. And you can tune and you can have high quality carriers. So this is just a few examples of recent results on silicon, and this is also a monolithic one. This is especially interesting because this is the overall device, and this is the RF chip and the optical chip. That can give you an idea of how big is one and how big is the other. The optical parts are usually very small, and the main problems are here in the RF part. Okay. Okay. This is a little bit more augmented scale. Right. So to finalize this part, and of course to give me some step to go into the next part of the lecture, I have to say that all these application-specific circuits were designed for a specific purpose. Okay. However, in some of these cases, the people who work on the chips realized that they could be used for more than one functionality. Okay, so there's one silicon nitride chip here, which was designed as a discriminator. That means it was to detect a phase modulated signal and then convert into intensity modulated. But then the authors were able to operate that as an arbitrary waveform generator for ultra wideband pulses, also as a Hilbert transformer. There's another example here, very nice one, which is made on indium phosphide, which was designed to be a 3-pole filter, okay, for microwave signal filtering. But then the authors were able to demonstrate this as an integrator, a differentiator, and a Hilbert transformer. So then the idea comes naturally as, okay, if would it be possible to have something which we could design and could be multifunctional, okay? So in the case of ASPICs, this is very difficult because when you really design a chip to do one functionality, is very hard to operate and do with it another functionality with enough quality, okay? And there's also something which reminds very much about the electronics, is that when in the early times of electronics, when you had to do one chip, an application-specific chip, and the early stages of development, it takes a lot of time and it takes a lot of energy and cost. To illustrate that, I'm going to borrow a biograph from my colleague Wim Bogarts from IMEC in Ghent. That gives you more or less a rough estimate of how much does it cost to design and have a silicon chip nowadays. If you usually, let's say, I mean, you have different options. You can go to a specific RAM for you, or you can go to multi-periodic wafer where you share the costs with other users. But these, more or less in relation to the time that it takes, is more or less quite a good estimation. You spend some months designing it, then you fabricate it with whatever choice, but it's usually not very easy to have your chip fabricated in less than 6 months. If you want to package, you have to add an extra 1 month. And if you want to test it, then it's like 2 months more. And sometimes things are not successful at the right time, so at the first time, so then you have to, what happens if you are, the chip is not working, you have to come back and do redesign. Even if it works, you want to refine it. You have to repeat it. And if you start adding costs, then it ends up to something which is very, very, very inefficient, okay? So what was done in the electronic industry? In the electronic industry, what we do now, in many cases, is we have like a suitable developing system like DSP, FPGA, etc. And we want to emulate a given circuit. We usually do this on an FPGA. We select one, we buy it. It's quite fast to get it. It's usually quite straightforward to program and test the chip, especially if you are younger. If you're old like me, it's not 4 weeks. It would be like half a year, for example. And of course, only if you need it, and if everything goes well, then you design the ASIC and you fabricate it, a specific one, okay? So basically, you use like general purpose circuits like FPGAs or DSP because they have some very, very desirable features as compared to ASICs. And you only do ASICs if you really need to do them. So this brings me to the second part of the lecture, which is the programmable multifunctional analog photonics. Okay. What is the idea behind this concept? Which is it's more or less to replicate the same thing in photonics with several precautions. I mean, we are not these programmable circuits are not going to deal with digital signals. They are not digital. They are analog. They are going to try to condition the signals in the photonic domain, so they alleviate some of the tasks that DSP should need to do later. And these are some examples of circuits that have already been developed and reported. And you will see immediately that are a little bit more complex than the ASICs that we have been considering, aspects that we have been considering in the previous view graphs. So what is the concept, which is it's very similar to that of FPGAs. In fact, it is quite a transversal concept. Does not only belongs to electronics. It is used in many other areas. Of course, electronics immediately shines the light of FPGAs and ASICs. But think about networks. How are networks operated today? They're no longer like ad hoc networks. People are working on having a shared infrastructure, a shared resources, which you program and attending to your needs to do something or the other. You increase capacity on a given part of the network at the given time because you're interested. There's a football match or whatever. There are a lot of people with their mobile phones or whatever. You provide more quality of service at a given time because it's required for whatever. And at the end of the day is having a common infrastructure and making it do what you want to do by programming. So this is actually what is behind the programmable multifunction analog photonics paradigm. It's exactly the same concept. So here what we want to do is to have or to fabricate something in integrated optics which is always the same. You fabricate exactly the same architecture and you provide then the programming so that architecture does whatever you want to do it, what you want them to do it at the given time, for whatever application. And it's a very trendy subject because you will see a lot of papers, probably there are a lot more in the last years in very high-profile journals, and because there are a lot of applications that could benefit from this approach. So let me try to explain you a little bit how this works. Now, if you consider that we have a lot of emerging applications that require flexibility, and we've been talking about 5G or whatever, then it is clear that if you have like a base circuit that you can program is very, very useful. But not only in telecoms. One could think, of course, of telecoms and switching, for example, but arbitrary mode converters, mode adapters, of course, for multi-core, multi-mode operation, okay? For microwave photonics and RF, of course. But then there is also a lot of activity in quantum information processing and doing all these things, all this kind of functional circuits. And I will try to explain you what is the rationale behind. And of course, for other emerging applications. And all these are like small samples that have been reported in the last couple of years, 2 or 3 years, if I'm not mistaken. Okay, let me pass this. Okay, so to do this, we need to have like a regular architecture, something that it's what we are going to fabricate always. And this is what we call the waveguide mesh. The waveguide mesh is like a mesh of waveguides in a given geometry, which has to be stated what is the best one. And the foundations can be found in 2 papers in the early 90s by people working on quantum information because they wanted to do some kind of universal circuit that could do any kind of linear transformation. Okay? And then more recently, they discovered that this could be done with a set of beam splitters, and more recently, Dave Miller from Stanford translated this concept into an order sequence of Mach-Zehnder interferometers which can be integrated in photonics. Right, so more than that, then you have like these realizations where you have these, let's say more or less regular arrays of interferometers. This comes from the more or less quantum information-oriented groups or researchers. These are like triangular mesh, and this is like let's say like a more rectangular arrangement of multi-beam interferometers. And the thing is that these structures are only feed-forward. Once you put your signal here, you have no possibility of feedback. Okay. we think that this much more interesting is to use this waveguide cells meshes, okay? So you could have like different alternatives, different geometries, and this reminds very much about solid-state physics, where you have your lattice and it repeats itself. In this case, you have pair of waveguides which are connected by Mach-Zehnder interferometers or by a mixing element, which we call the tunable basic unit. And you can either consider this square, mesh, or hexagonal, triangular, etc. By the way, now that Peter has referred to the soccer ball, you may remember that the soccer ball is composed of 20 hexagons and 12 pentagons. Okay, because this is the best geometry to have a round surface. And it turns out that you have these alternatives to do two-dimensional waveguide meshes, and it turns out that the hexagonal one is the best one for many reasons. Because if you trade off with a given set of figures of merit in terms of number of elements that you use, etc., it becomes the best. It's not very evident, but it becomes the most efficient one. But anyway, you could do like this, and you replicate this, and this is what you would fabricate, okay? And then the question is, how do you operate this to do different functionalities? So the key is resides on how you operate this tunable unit here. This is like a Mach-Zehnder, and you can put either it could be a directional coupler, or it could be a tunable 3 dB Mach-Zehnder, where you use two different phase shifts, okay? And depending on how you operate these two phase shifters here, you can either use this unit as a crossbar switch, or, and this is the important difference, you can do it as a tunable coupler. You can use it as a tunable coupler with a coupling ratio in between 0 and 1. And the most important feature, in addition to that, is that because you use two independent phase sources, you can not only program your amplitude or power splitting ratio, but you can program an independent phase shift. This is very important. This is where the key concept resides, because you can do independent programming of the amplitude and the phase. If you do that, okay, then you are able to really build very, very complex circuits. The ones I'm showing you here are feed-forward only circuits, which have been reported using triangular interferometers. This is an example reported by Dirk Engelund's group in MIT. This is for the emulation of a linear transformation to support a neural network, okay, for vowel recognition. There's another example here that is used for a simulator of quantum transport mechanisms, and by changing your Mach-Zehnders here with the ability of putting this independent phase and amplitude setting, then you can emulate here different quantum media. So this is quite useful for people working on ICTs, on trying to artificially implement different propagation media. Okay. Finally, in one of these applications, let's say more practical or more connected to transmission, this is a mode unscrambler, a 4-mode unscrambler using a triangular interferometer to separate 4 different modes from an optical fiber, which, as Peter has mentioned yesterday, in the talk before, they are orthogonal, so you need some means to select the different modes, and obviously in this case would be by spatial addressing different ports to select to send the information signals from each mixed mode to different output ports, and that way separate the information content. And this is also like a mode transformer. And yet, these are, as I pointed out, feed-forward only circuits. Now, if we consider now the other more complex structures where you have the possibility of having feed-backward signals, like feed-forward, feed-backwards, I'm going to show you some experimental results which can give you an idea of what is the capacity of these circuits. Now, the idea here is that if you integrate this into a signal processor, you can do quite a versatile. I'm going to try to show a video here, if it works. I think I have to go back here. Okay, right. Okay, the idea here is to use this mesh and embody there into a more general system where you have inputs from potential RF input signals or either optical signals. And you have like 4 different modes of operation. In the electrical, you have electrical inputs. As I explained before, you do the processing, you down convert, and you do the electrical output. That would be the typical RF photonic operation. But then you have electrical optical one, where you have your signal probably from your antenna, you do the processing, and you don't want to down convert here, but you want to send it to another location because you want to do some remoting of whatever. The optical electrical mode would be you have an optical input, maybe from a coherent system, and you want to do some coherent detection or whatever, or preconditioning or whatever, and then you go into the electrical output. And then the final operation, of course, is the optical, where you just use your optics as a standard filter, as a standard processor, without having any coupling with the RF inputs and outputs. Okay, so this is the way. So the important thing is the reconfigurable optical core. So by exploiting what I've been mentioning before, that means you have a wide web of a wide mesh of reconfigurable elements, each of which you can independently program amplitude and phase. Then you can do a lot of things. For example, this is an example of a waveguide mesh where you use several cells that you have here. You don't use any other. The ones that you see in blue color are not used. The ones in orange are in bar state. In green are used as a tunable coupler. And in black is just a cross switch. So then the same structure allows you to do different functionalities in terms of filtering, for example, but also allows you to do other functionalities. Can do a multi-port interferometer, for example, is emulated by this. So you still you have finite impulse response, infinite impulse response, multi-beam interferometers, which can give support to the main functionalities of microwave photonics, for example. This is a way to program the meshes so you can do the different functionalities in a chip that correspond to different RF photonic operations. So you could, in principle, do many of these with the same chip. And of course, if you go into the experiments, this is an early demonstration of the concept, which is done in a square. That was a very simple demonstration in silicon nitride with only 2 square cells. And with that, I mean, by activating the Mach standard interferometers, very basic filtering configurations were demonstrated, but gives you a little bit of idea of the potentialities. And finally, I'm going to explain a little bit more complex experimental result, which is made using an hexagonal cell, and in this case, it's a 7-cell structure. So it is quite limited. Okay, so it's not very highly functional, but yet, as I will show you here a little bit later, it can do a lot of things. And this is more or less the prototype that was fabricated. The chip is here. Then this is the PCB, the connections. I'm going to have like a zoom here, where you can see the hexagons here. These are the hexagons, the Mach senders. These stars are trenches to avoid the thermal crosstalk. And all this is the wiring. Of course, this is a very simple circuit, so it doesn't have yet different layers, okay, for wiring. But nevertheless, it's very curious because with just this very simple structure, in this case, we were able to program more than 30 different potential or different functionalities. The potential was over 100, but we didn't have enough current sources to bias the chip, okay? So, but you can do a lot of things, okay? I don't know how much time.
3 minutes.
3 minutes, okay. I don't have time then. I'm going to show you some examples. All these are experimental results, okay? So these are like using the mesh to bias to do a lot of things. This is a cascade of Mach senders, a transversal filter, a ring cavity, a double ring cavities, and you can do tunable delay lines by selecting the paths. You can do also different outputs, and you can do like small beamforming architectures, okay? So since I don't have much time, then you have a small example of an interferometer. We have 4x4 as well. So all in all, this allows you to do basically any circuit emulation that you want. As I said before, finite, infinite response filters, multi-port non-recirculating interferometers, arbitrary transformers, whatever. So you can do almost everything that can be defined by a unitary matrix. And if your matrix is not unitary, then you can use another technique which is called the singular value decomposition that allows you to do any kind of matrix as a cascade of 3 different matrices. 2 of them are unitary, and the third one is a diagonal one. Okay, I'm going to stop here, but just to give you or refresh a little bit of the applications that if we are able to successfully develop these implementations would enable us to do. And the list is, I mean, I just shortlisted some of the applications, but there are a lot of functionalities. And I want to stress again that it's not the digital signal processing. That would be something that you do in optics to alleviate the load that you have to do on the final stage if you're carrying digital signals or whatever. So I don't have much more time. If you have any questions now or later, I would be very happy to try to answer them. Thank you.
Thank you very much, Professor Capmany. The reason that we need to go into the end is because the people in the palace finish their journey in 6 o'clock. Okay, so this is the reason. But not because the interest of the talk was very, very high. So I must to say one additional word about Professor Capmany is that Professor Capmany is not only a good engineer and a very good scientist, but in addition, he is also very, very good entrepreneur, because in order to do this kind of topics, he created one company in Valencia area, okay? So as people before, the people in this room, the invited speaker of this room in this day are all of very complete profiles. So a few questions, please. Any question? Please, one.
The speed of this operation is again we limited
restricted by electronics and
Well, there are certain, my last part of the talk, which I cannot cover, are the limitations and the challenges that you have to overcome, okay? There are like 2 or 3 main limitations. One is losses, okay? Which of course, that means that to be able to do a functional circuit, you need a reasonable number of cells, okay? Like at least 20, 25. So each cell, in particular, the ones that I've shown are passive, so insertion losses accumulate. So there's one of the limitations is to reduce the insertion losses by passing through the Mach sender, okay? And we are working on that. The second thing is about speed. Speed is, of course, in this prototype, we use just thermo-optic switches, which are slow. But of course, you can use other, and power consuming, of course. And you can use other approaches. Faster approaches would be based on carrier extraction, okay, for example. Low power consumption approaches should probably need to resort to some kind of capacitive switching mechanism, okay, whereby you only consume power when you are activating your capacitor and it discharges, but in the meantime it's not consuming power. So that means that you should resort to some kind of, let's say, like piezo mechanical or MEMS kind of mechanism. And well, there are certainly, this topic has is incredibly challenging from the engineering point of view. I mean, there are a lot of things that have to be solved to evolve this concept. The other one is the wiring, the multi-layer wiring. How do you program this? How do you develop your software so you can scale your circuit analytically? It can be done, okay? No numerically, because you need very fast algorithms. So you need them to be, if you want, if possible, as analytic as possible, and this can be done, of course. And the other challenge is controlling the status of the circuit. We've shown a big mesh where you have a lot of phase shifters, and this will, I mean, inevitably will evolve in time, and the circuit will drift from the ideal operation. And you don't want this to happen, of course. So there are ways to control your circuits, but to do this, usually you have to tap or monitor your optical signals. This is not good news because you are again losing power. There are testing techniques which are capacitive, and they rely on the changing of photoconductance of the waveguides, and these do not consume power. But again, you need a sensing element per waveguide or per modulator or per Mach sender interferometer. So there's another alternative, which is to do some kind of smart multi-parameter testing, where you do some refreshing of your circuit, like it's done in electronics. And for that, you need like machine learning techniques. So all the circuit is expected at a given time, very fastly. All the sets are done, and then you can continue operating. So these are the main basic limitations, as far as I can remember. There might be others, of course. Thanks for
Okay, any other question? Well, in this case, we are going to close the session and the debate. And please remember that tomorrow, well, let's thank us again to Professor Capmany. Please remember that tomorrow we have a very interesting day, because we are going to have the first talk, 9:30 tomorrow. with Professor Pendry concerning the light in the nano dimension. That is becoming a key issue in the future research. And then we are going to have another 2 additional very, very visual talks in the rest of the morning. And in the afternoon, we are going to have a very, very interesting round table with five members, okay? So concerning challenges in this kind of topic. So tomorrow you are going to have the opportunity to ask every question you consider convenient to the best people worldwide in these topics. So thank you very much and see you tomorrow.